Working. Okay, welcome to day 3. Looks like we're about ready to begin. The first talk is part 3 of Gergely Bérczi's mini course, and today the focus will be applications to jet moduli spaces.
Thank you very much, and so I will start this third final talk with a short outlook on related results, and just to put our theorems into a broader context. And then followed by this, I turn to applications, and in this, today I will basically focus on reparametrization groups and enumerative geometry applications. So in more particularly, we will work with the jet moduli spaces and see how we try to highlight its central role in geometry and in classical problems through some examples and results. So that's the plan for today. So let me start with, as I said, just a little bit of overview of the context where these theorems actually sit. So this, let's say this theory, I have 3 main components. So the first one is really the construction. So this is just a very quick reminder again. So you have a non-reductive, so we have a linear algebraic group H complex, written as a semi-direct product of its unipotent radical and the radical group and the reductive group. We have a polarized variety and action of this on that. And we assume that this is a well-adapted action, meaning that we use a character to position the origin in the right place. And we also assume that the stabilizers are trivial for the U action on Z min, the minimal weight space. And in this case, we have this construction that tells us that the invariant ring is finitely generated. The project of the invariance gives something which we really like. So this is what we expect really parameterize these orbits. And we can describe the semi-stable equals stable locus in this very simple way, which is kind of corresponds to the Hilbert-Mumford criteria in this situation. So how this fits into a broader context. So as already was explained by Johan and also yesterday by Thomas, there is this so-called Beyond GIT program started some more than 10 years ago. By Jared Apper, Daniel Happen-Leisten, Johan Hengloff, and others as well. So it started with this beautiful observation that construction of moduli spaces can be put in a more general context using stacks. So we have moduli stacks M, and inside that, again, we just sort of, this is just really a very rough description of this because it was already explained, but the idea is that we can, after choosing an ample line bundle, this gives you some numerical invariance on the filtrations, and so we can define a semi-stable locus for this moduli stack and the good moduli space, if we can. So Apper came up with this definition of good moduli space, which is really an extension of the idea of a coarse moduli space in GIT. So the point is that once we have this setup, we often we have a theta stratification, and this theta stratification when we started with a quotient stack, it really coincides with our GIT stratification. So that's really extension of this idea of how to stratify moduli spaces based on instability. So in particular, if you have this quotient stack, which is just a semi-stable locus mod G, and the quotient map to the GIT quotient, it's a good Moduli space. And as I said, the theta stratification in this case coincides with the GIT stratification. So the problem here is that, as far as I know, there's no extension of this really nice theory for non-reductive setup, just because all the kind of, by the definition and by the assumptions, really assume that the stabilizers are reductive. So there is a ongoing work by David Reed, who really has really nice results towards an extension. He tries to extend this notion of good Moduli space to non-reductive quotient stacks. But as far as I know, so far there is no analog for theta stratification. But it's Johan who can actually correct me. So I would like to mention that this theorem, which we originally used this, we never, as you see, I don't use the stacky language, but it was later really reproved and generalized by a student of Johan, Ludwig Modin, and his paper from last year. And that generalization works over any characteristic. It also works for actions in families and in this setup also for general theta strata. So. And also there is a extension or a refinement of the theorem for affine situation. So during my talks today, this week, I always assume that we have this polarized setup. So I work with projective varieties. Of course, in many applications, the starting problem is really, it's an affine Moduli problem. So one solution for that is we try to, which very often doesn't work, or it's not so easy to see how it works if you just really turn the affine problem into a projective by taking some projectivization or projective completion of the original parameter space. But there is also a theory, like the extension of this theory developed by Hamilton, Hoskins, and Jackson for affine non-reductive GIT. So there's a paper about this, who someone is interested, and also in particular application of that for representations of fevers with multiplicities. Yeah. So that's just kind of my comments on the construction, and the second component of this theory is let's say what happens if semi-stability is not equal to stability. So how this GIT blow-up procedure extends to a non-reductive case. So this is what I explained yesterday, that it's kind of after many iterations, it seems to be like we arrived to a construction which works. So, but there is really nice and beautiful work for special cases before this this happened. So for additive group actions, Yikun Kiao has a paper, actually has two papers about kind of construction of an iterated blow-up. It's an iterated blow-up algorithm, right? Ours, using some sort of fitting ideal centers. So the centers of his blow-up procedure is non-reduced, and so it's kind of less geometric, but and it works for weighted additive groups. So there's some sort of restriction on the group class, where it works. For parabolic groups, which is again like a very common situation, which we work with in Moduli problems, and in this Moduli problems where the symmetry group is a parabolic, or parabolic is involved, very often, I mean, semi-stability is very rarely equal to stability. So we have some semi-stable locus, so the stabilizers are non-trivial. And there is a procedure for this specific case, which was worked out by Vicky Hoskins and George Jackson, and in this paper, where they specifically study what we can do actually, how to get rid of stabilizers from this parabolic case. And finally, let me just mention the last part, which is the most relevant to me and especially from the last 5-6 years work of mine, is the cohomology of quotients and the non-reductive moduli spaces. So in particular, integration on these and intersection theory of these quotients. So when you say in this nice situation where stability equal to semi-stability, the quotients are smooth projective spaces. So we talk about ordinary intersection theory. If we don't know anything about this, but don't know too much about the situation when this condition doesn't hold, so the quotient might be, singular. So, and then of course you can study intersection cohomology theory, but that's something which is not worked out yet. So, and there's this very general question, which actually also came up during discussion this week. So is there any sort of stacky integration theory in the presence of stabilizers? So can we somehow get a better, a more elegant way of this integration theory for at least for quotient stacks when we have stabilizers, non-trivial stabilizers, and that's kind of something which I believe is missing. Okay, so this was a kind of an outlook before I turn to the applications. As I said, my main focus today is a class of non-reductive groups, which I call reparametrization groups, and I already introduced in my first talk. And this kind of group and the corresponding moduli space, which I studied, this is moduli of jets, I explain in a second. They have seen a lot of applications in the last few years, and just really the goal here is to highlight their central role in classical animative geometry problems. So if this is a little bit of beyond the main theme of this conference, so I really apologize for that. But I just, this is the goal here, is just give some sort of a survey of these ideas, which central and core part is this very special and very simple non-reductive group, this reparametrization group. So the motivation is, as I said, so this is what I told you, like if you have a complex manifold and the jets of holomorphic maps is just basically the set of, you can look at the holomorphic maps from C to X and the moduli space. And that's really occupies a central role in animative geometry, as I will explain. So what are these jets? So instead of taking entire holomorphic curves in X, we can take just jets of holomorphic maps, because we know that these holomorphic maps might not exist or they degenerate. This is kind of this hyperbolicity question. So if X is sufficiently positive, these maps do not exist, and like entire holomorphic curves. But we can always work with the algebraic version, which is just some finite jets of these holomorphic maps. And so in this, what is that? The jet is really just, you take the first k terms of some Taylor expansion. So you take the first, second, and k derivative of a map to C. So you take it locally, right? So you take a local chart on X, which is just Cn, and then we define jets in Cn as jk1n. This is my notation for that. So jets, k jets for maps from C to Cn, that's 1 and n. So just really just given by the first k derivative. So it's basically a vector space of dimension n times k. Now, what makes this interesting is that if you look at this vector space in this form, so it's a jet, then we can reparameterize the source C, right, phi. But in this case, we use some sort of this diff k is a shorthand notation for jk reg 1, 1. So this is the local reparameterizations of C. In other words, you take polynomials without constant terms or zero constant term, And that really gives you a reparameterization of C at the origin. So let's see how about, so this reparameterization of the source space gives you a reparameterization of the jet. So that's the action. And so here's, which I already showed in the, on Monday. This is a very simple calculation you can make. So you take a reparametrization element, and you take a jet, and then you compose the two. So we substitute. You see that we have this weird matrix group coming up, which is really a U hat. It's a C star extension of its unipotent radical. It's generated or parameterized along the first row. And it has a C star along the diagonals. It's upper triangular form, and we have explicit description of these polynomial entries. So it's non-reductive, and now what you can do, so what we call really the moduli of jets, so it's this quotient, JK1L mod diff K, whatever it means at this level. So it just says that we talk about orbits of diff K on this space. Of course, later we can take several different kind of quotients, but for now it just means that this quotient is the moduli of K jets of germs, or the moduli space of jet moduli space, right? It's always a jet moduli space of order K. Right. So this is a very simple object. Now you can do this in families, right? This is what we call jet bundles in the literature. So if you take maps, so if you take a holomorphic map from C to a jet of a holomorphic map from C to X, and in local coordinates we can write it. We have n local coordinates, and the K-jet bundle is really just is united by JKX, is the set of these jets F, and there's a natural projection to X back, which is sending a jet to its value at 0. So this is, for now, this is the set. But how do you define this in like a topological way? So this is really an associated bundle to the principal diff X bundle over X, diff X. So this the structure group is the, so this is a principal bundle with the group is the set of all polynomial reparameterizations of X of C, if you have n dimension n of Cn at the origin, right? That's a non-reductive group, but they still have a principal bundle over X with that, and then we associate to that this jet space, which is just a vector space. So you can describe this bundle as in this topological way as an associated bundle, and you see that the structure group, which is this diff Kn, this is non-reductive. So this means that we have a non-reductive structure group for this bundle. So this is not a vector bundle in particular. This is not a vector bundle. So the jet bundle is not a vector bundle. And if you go back to and read papers about the jet bundles, if you go back, there is this seminar paper of Jean-Pierre Demaille in the 1990s, it's a proceedings paper which actually is beautiful. He describes this bundle and beautifully computes the transition functions for this bundle, and really calculates these transition matrices, which turns out to be it's a non-reductive group. Yeah. Diff X is, just think of that as a principal diff bundle over X, where the group is this group here. Diff Kn is the group of polynomial reparameterizations of Cn at the origin. So it's not just linear reparameterizations, that's GLN, but you take higher order polynomial reparameterizations. And the verse, yeah, and yeah. Now, if you have a map from, so you have a holomorphic map from C to X, that certainly induces a section. Sorry, it can be lifted to the jet bundle, and also diff K acts fiber-wise with fibration. So the point is that this is really a fibered version of our previous quotient. So there's a fiber-wise action of this. You remember, this diff k is the polynomial reparameterizations of C. So we can reparameterize this C, that's denoted by diff k, and that the fiber of this bundle is this jet space, so it acts fiber-wise on this bundle. So we can take the quotient. And that has something to do with jet spaces and arc spaces, which I will not explain here because it's kind of not really relevant. I just really want to save some time. Anyway, so the projective completions of, we talk about now this jet moduli space, and we have the idea is that there are different compactification and projective completions of this quotient, which play central role in different enumerative geometry problems. So I've tried to put down a map here. So we have this quotient here, which is, let's say, quasi-affine. If you look at that, it's a quasi-affine variety. But of course, let's start with the middle one. You can actually take some projective completion, let's say the simplest one, projective completion of the jet space, which is just a vector space, and take the non-reductive GIT quotient. It turns out that in this case, you can select the grading one parameter subgroup. After one blow up, it's enough to take the first blow up along that projective space at infinity, which we added, and then after the first blow up, we have semi-stability equals stability. That's kind of a nice picture. So in this case, the blow up procedure is very simple. And that was like a crucial fact in this application of this theory for the hyperbolicity theorems. So that's something which we discussed this week. But there are two other compactifications which turn up in the literature. So the first one is, let's say, this Desmaillet sample bundle. Okay, I think I will just go as I've written on the slide, because if we go in this order. So let's start with the first one, right? The first one is, it turns out that this, when you look at, just assume that you have Cn and you take jets of curves in Cn. So imagine that you are the origin and then you take jets of curves. So what it can encode is a kind of a point on the Hilbert scheme of points of when the order of k is k plus 1 point supported at the origin. So there's a component of the Hilbert scheme. So this Hilbert scheme of k plus 1 point on Cn, that parameterizes ideals of co-lengths k plus 1. And there is a subset which is called the curvilinear locus. Those are the ideals where the quotient is isomorphic to this curvilinear algebra, t times ct over t to the k, which kind of says that if you look at this space as parameterization of configuration space for k plus 1 points on Cn, then if the points come along and together at the origin and along one smooth curve, then you get a point here. So these are the points where the points come along a smooth curve. So this curve is actually given by this jet. So if you take the closure of that locus, that's a component in the puncture Hilbert scheme. That's called the curvilinear component, and that's a small component. You will see in a second. So this is a completely different. This is a different compactification than the non-reductive GIT quotient. This is singular, this component, and projective, and don't be the tautological bundle. That's very important. So the key power here is that there's a tautological bundle which on this compactification, which does not exist over other compactifications. And there's a tautological intersection theory which encodes enumerative geometry problems. So I will focus mostly on this tautological intersection theory in the rest of the talk. So this tautological intersection theory encodes enumerative geometry problems, and so arithmetic geometry important. Now the second one is this non-reductive GIT quotient. As I mentioned, this is we know that it's enough to take one blow up, we get a non-singular projective variety, and therefore we have this Jeffrey Curven type Jeffrey curve and residue integral formula for intersection theory, and that helped us in proving some polynomial hyperbolicity conjectures in the past. And finally, there is a third compactification, which was the first one actually historically. So Jean-Pierre Desmailles and his school actually studied this jet bundle extensively since the 1990s. And the reason for that is that, as I will not explain today because it's not the topic of my talk today, in the hyperbolicity question, this plays a central role. So you can reformulate hyperbolicity questions into sort of intersection theory problems over this Desmailles bundle, which is another compactification of this quotient. So it's again a non-singular projective space. I mentioned it's used traditionally and historically in hyperbolicity questions. And it turns out the intersection theory of this bundle, which is really nice because it's just an iterated tower of projective bundles, is sort of less efficient than the non-reductive GIT quotient. And that's that really just tells us that this Jeffrey curve type, so the integral theory on this quotient is somehow more efficient than integral theory on this other one. I just leave it in this way because this is not, I don't really want to go into this. I really want to focus on this first type where we talk about intersection theory and tautological intersection theory on Hilbert scheme of points. But it's important to know that you can ask immediately the question for the relationship between these, or for these all birational compactifications. There's no map from any of these to the other, first of all. So it's a non-trivial birational transformation going from one to the other. And in fact, it's really hard to construct. So there was an attempt by me and Damian Brobeck to construct like a resolution of the Desmailles bundle and construct a map to the Hilbert scheme of points, which didn't work. And I have a paper which constructs a resolution of this non-reductive GIT quotient such that has a morphism to the Hilbert scheme of points. And that's a highly non-trivial resolution process, which is really, really combinatorial, and there's no general formula actually for that for any k. But if that exists, then we have actually, you will see that somehow tautological intersection theory here is understood and we have formulae, but we have some unknown components of the formulae. So understanding the map from here to there would immediately imply closed and full formulae for these enumerative geometry problems. So construction of that morphism is kind of an important question. Okay, so let me then talk a little bit about Hilbert scheme of points. This is absolutely off topic, but anyway, it's something at least I hope is refreshing. So we have the Hilbert scheme of k points on Cn. It's really the set of ideals in this polynomial ring where those colang's is k, right? So we know this object. And then let's say with this side, this is for n equals 2. So this is a Hilbert scheme of points and surfaces is a non-singular, irreducible non-singular variety, very much studied, and this geometry is really, really, we know a lot about this geometry, right? But when n is at least 3, we know that this Hilbert scheme is non-irreducible. We have components, but there is a distinguished component which I denote by G Hilb K Cn, just because it's a geometric component. It's the main component. This is really the closure of the reduced part of the space, so that the points are all different, and then you take the closure of that locus. On the other hand, we can look at the punctual side. So 0 here, this lower index 0 always means punctual. So that means that we're talking about ideals supported at the origin. So these are the puncture Hilbert scheme is just one supported at the origin. And then there is a component G Hilb 0, which is the intersection of that with the main component. That's everything. This is non-irreducible. This is non-irreducible. And finally, this curvilinear puncture Hilbert scheme, which I mentioned before, that's a component here. So it's a smoothable component of the puncture Hilbert scheme. And it's a small component, so conjecturally on dimension 3, this is the smallest puncture component, for instance. So the geometry of, series and surfaces, everything is nice. The Hilbert scheme of K point is a smooth of dimension 2K. And the puncture Hilbert scheme is irreducible and of dimension K minus 1. This is a highly non-trivial fact. This was actually the thesis of Briançon it's still the proof. There's no alternative proof. I mean, I'm not aware of alternative proof of this. Anyway, so this is the puncture part is irreducible. It's singular, but it's irreducible, and moreover, complete intersection. But it's just cut out by bundle, which is called it's a tautological bundle actually, and in this case, the puncture Hilbert scheme is really cut out by this bundle from the full Hilbert scheme. It's kind of important in the tautological intersection theory. Okay, so for n is lattice free, this is we have a very pathological behavior. So we have Vakil called it the Murphy's law, and we have components, we have singularities. The deformation theory is not understood and, in fact, out of reach. So here's my picture. This is which I really like about Hilbert scheme of points. This is from basically Joachim Jalisiev's PhD thesis, what he calls, and I call the Bellis Hilbertis. So this is a Moduli space where we don't understand too much, but you know, we start with a stem, which is this main component of the Hilbert scheme. And you see what I indicate is that any ladybird indicates a point in the Hilbert scheme, and that the dots somehow indicate that the point arrangement. So in this case, in this stem, the points are all different as the main component. Now there are some other components which are the petals. And we have two different colors. The yellow petals are also components of the puncture Hilbert scheme. So these are puncture components. And some of them are smoothable, so they sit in the boundary of the stem. And the dark yellow curve here, which is a smoothable component, puncture component, it's a yellow curve. So it's a component, but sitting in the closure of, so in the stem, that's the curvilinear puncture, the curvilinear Hilbert scheme, right? So one of the interesting facts and highly non-trivial facts about this is a deformation problem is that kind of answers an open question: how the torus fixed point. So if you have a torus action on C and that induces an action on the Hilbert scheme, how the torus fixed point, in other words, the monomial ideals, distribute over the different components. They all sit in the stem, but it's not clear what the distribution of them among the puncture, about the puncture components. And it turns out that all the monomial ideals sit in this very small curvilinear component. So any monomial ideal has a deformation into a curvilinear algebra. Okay, so this is a sophisticated object, right? And the point is that this is a compactification of this non-deductive quotient, where we have with a very important geometric component, which is this tautological bundle. So whenever you have a bundle over your variety X, it's like a rank R bundle, we can associate a rank R times K bundle, VK, over the Hilbert scheme of K point on X. This is a rank RK bundle, and this works in general. So in any dimension. So the fiber actually how you think of that is just you look at the space of sections of the original bundle over the subscheme, and that's a rank arc. It's a dimension arc-dimensional vector space. So that's the fiber over the point psi on the Hilbert scheme. So tautological integrals, what are these? Oops. Whenever you have any Chern number, let's say of a vector bundle or this tautological bundle, we can ask for, this is what we call tautological intersection numbers or tautological integrals. We can integrate it over this main component, right? So now we talk about only integration over irreducible. So it's not virtual integration, not yet. So that's something which we work on. But for now, we can pick one distinguished component of the Hilbert scheme. This is the main component, and integrate any form over that. And these are called the tautological integrals. More generally, and that's very important, we can define so-called geometric subsets of the Hilbert scheme. So, and that's kind of this is kind of sort of universal subvarieties which kind of encode a lot of the enumerative geometry information. So let's see, if you fix a set of finite dimensional quotient algebras, let's say A1 up to AS. So the dimension of AI is Ki, and they add up to K. And we can take this Hilbert scheme of points on Cn. Why did I change from N to M? Sorry, this is N here. N. So I denote it by Hilb A1 dot AS Cm. So what is this? Imagine that you have on Cn, we have S points. And at each point, in the first point, I put a subscheme of type A1. So A1 describes your quotient algebra. So it's this type of this. In other words, this is a point which is isomorphic to this quotient, this algebra A1. And then the second point, I put another subscheme which has type A2. And in the S point, I put one more which has type AS. Now, this is the open part, right? So we can do that. And we can take, this is a subset because we have K is equal to K1 plus K2 plus Ks. This is a point in the Hilbert scheme of K points of Cn. So we can take the closure of this locus, and that's what we call the geometric component corresponding to this tuple of algebras. So, for instance, the main component is really just the geometric. This corresponds to the algebras, the trivial algebras C, K times. And if you take, for instance, if you take the Curviner Hilbert scheme, so in this case, I did not put a 0 there because the support can move on Cn. Then if you take the algebra AK, which is C2 mod T to the K, then this is really, this is what we call the Morin algebra. Then the corresponding geometric subset is the Curviner Hilbert scheme. And there is a beautiful theorem from 2013 of Jörn Lennemo to prove this theorem first, that this is kind of fits into this general principle of enumerative geometry, that we have universal formulas for enumerative questions. So in this case, it says that if you integrate, this geometric subset is, it's a nice irreducible, not necessarily irreducible, but it's the geometric part of that. We can take again the closure of the open locus. So that's an irreducible component. So if you integrate over this irreducible component of any form, then there's a universal polynomial. This is P A1 A to AS. It only depends on the types and the topological numbers of the original of X and the original bundle V. So it will not depend in any other way. So there's a universal polynomial which gives you this intersection number in as a polynomial of the Chern roots of X and V. And so his proof is a kind of a beautiful but non-constructive proof. So it doesn't let us give formulae for this. So the question is how you calculate such an integral. And by the way, there is another proof by Lee saying that this is using algebraic cobordism theory. But neither of these give you formally, so sort of starting like 10 years ago and in the last years, I was working on this problem of finding formulae for such integrals, and in some special cases which are related to enumerative geometry problems, I will explain. So the broad question is how to calculate such an intersection number. And so first of all, we can start with this small component, this curve in a Hilbert scheme. So there is this is a generalization of my thesis in some sense. We can work out an iterative residue formula on this integration on this curve in a Hilbert scheme, which can be turned into a toric residue formula using this non-reductive GIT model, which I explained, so, and construction of the map from one model to the other. And then with a joint work with András Szenes, we kind of work out a theory, we develop a theory which reduces integration over this main component of the Hilbert scheme to this very small puncture component of the Hilbert scheme. So that's kind of a surprising fact, which so there's many other results, recent results, indicating the fact that somehow the topology of the Hilbert scheme of points is encoded in this very small component and its neighborhood in some sense. So, you know, one aspect of this is that, as I mentioned, this is result with Jonas Svensson, is that all torus fixed points sit in this small component. So that's a good indication that somehow the topology is really concentrated, so kind of determined, or I don't know what I'm the topology, like the intersection numbers, let's say, somehow are concentrated and determined by this small component, and it's embedding into this Hilbert scheme. Okay, so in the rest of this talk, I will just list 4 different problems, where we see applications. In each of these problems, it is all kind of classical geometry problems. The answer can be formulated as a certain tautological integral on some geometric subset on some Hilbert scheme of points, right? So that's, and I will not explain the formulae, I just tell you, I just get to the stage where I put down the formulae, which presents this answer as an integral, okay? And this is just indicates how these quotients and these non-deductive moduli spaces play this central role in enumerative geometry. So let's start with the kind of a circle of ideas and the problem which is a central problem in global singularity theory is what we call, let's say, calculation of monosingularity classes and multisingularity classes. So if you have a map, a holomorphic map between 2 complex manifolds, M and N, N and M, with dimension N and M, so we assume that it's a positive codimensional map. So it's generically injective. Then, of course, if it's generically injective, it still doesn't mean that the topology, the global topology, might and actually will force some singularities. So if for a generic map, the question is, if I fix some sort of singularity type, can I determine the locus with of this singularity for the map? Can I, in N, right? So can I sort of like this degeneracy loci in N, can I determine it? What's the cohomology of that? So in a very specific case, you take the Morin singularity locus. So we take this algebra A, which is I denote, so this is the Morin algebra. And we take those points in N, where the kind of the local algebra of the map. So in other words, if I take the local form of this map, then this local algebra is isomorphic to A. So in other words, the singularity type of F at this point P is given by A. Now, if N is common, F is sufficiently generic, this is an analytic subvariety of N. This is the first observation of Tom. And moreover, Tom in the 1950s proved that, in fact, this class, which we know by, so this, you have this sigma A now. So this is a set of points in M. I'm so sorry, this should be K minus 1 in this case, but this A is for any algebra. So this degeneracy loci, so this determines your homology class in N, and it's a polynomial in the Chern roots of the difference bundle, right? That's kind of a really nice structure observation. So calculation of these, and that's why we call this, this is a polynomial, so we call this the Tom polynomial. And calculation of these Tom polynomials is hard. And it's kind of, it's a major unsolved problem in general. But, you know, there are some special cases, for instance, Runge formula, which we all know, is when you take the simplest possible, so we take the, what's the singularity locus for this map. It corresponds to the type A1. That's, so in this terminology, it's just sigma 1. And the singularity locus for a generic map is given by the Chern number of the map F. So in the difference bundle, where we take the codimension plus 1 Chern number of that. So this is the Runge formula. So there is a, I will not put down it's a huge and long literature of this problem. And I will not even put down our result. I'm just saying that we indicate that this question can be reformulated, not reformulated, but yeah. So that's part of the result with, this is my PhD thesis and the paper with András Szenes, is that the Tom polynomial of the AK minus 1 singularity is actually really a tautological integral over the Curviner-Hilbert scheme. So you can rewrite this Tom polynomial as an integral of some order class of some tautological bundle over the Curviner-Hilbert scheme, right? So that's kind of the first incarnation of this principle, which I'm talking about, that this problem actually has a enumerative, intersection theoretical description using tautological intersection theory of the Hilbert scheme. So in the last 5 years, actually, we've been studying this generalization of the same question for multi-singularity cases. So in this case, let's say just multi-point locus of maps. If you have a map from N to M again, we can define this Kleiman locus or K-Ford locus. So this is really just the set of points in M, in the target space, where the pre-image has, the fiber has at least K points. So we see this as a generically finite map because it's positive codimensional, and we can look for the K point locus of the map. This is the K-Ford locus, right? And again, this is the question is what's the cohomological interpretation of this locus? So, for instance, the double point formula has this form. It contains push forwards of ones and so kind of two terms and this kind of center part of the formula, which is a Chern number again of this difference bundle. So it's a Tom polynomial. It turns out to be a Tom polynomial, this is kind of this theorem which I state here is very rough, and this doesn't cover the truth at all. So it's not correct, but at least it's kind of an approximation. So what I would like to see, what I will write here is the following. So if you take this MK is going to be a sum over partitions of K. And for each partition, we have a product of MIs where the I's add up to K. So like belong to the partition. But the components of the formula is given by integral. So any component of that formula which we have is a tautological integral over now the main component of the Hilbert scheme. of a tautological bundle. So you see there's a similarity here, right? But it's highly non-trivial actually going from here to there. So this problem is significantly harder. And the reason for that is you see that it's a global problem. You can't really look at it as a local problem, like you can't really, because you kind of work with multi-point locus. It's not just you just can't just take one point and the local behavior of the map there so that it allows you to have the fibration. But in this case, you have to handle it as a global problem, and that's kind of somehow mirrored in this fact that the integral here is not about is not over a fibration. So this is really a curvilinear Hilbert scheme. This is a fibration over it fibers over Cn, according to the subport. But this one does not. So this is really the integration over the main component of the Hilbert scheme, which is highly singular. And we don't know too much about that. But somehow the theory says, and what we developed, that this integral can be reduced integral over the curvilinear Hilbert scheme. It's kind of there's a process of reducing the integration to the curvilinear Hilbert scheme. Okay, so the remaining 5 minutes, I have these two other problems. These are even probably better known. This is called curve and hypersurface counting. This is a classical problem counting nodal curves in sufficiently ample linear systems, and in general counting curves with given singularities in a linear system. And we can generalize it actually and take some counting hypersurfaces with given singularities. So the problem is the following. So we have a surface, let's say just the simplest situation, we have a surface and we count nodal curves, okay, in this situation. So assume that we would like to count the number of S nodal curves in a sufficient ample system. So we have a generic family of curves sitting over the right dimensional family. So it's a right dimensional base, and it's sufficiently ample, and we would like so that it has the right dimension, so that the number of these curves is finite. The question is, what is the number of these curves with the number of nodal curves with S nodal singularities? Exactly S nodal singularities. So Gergely has a really nice topological reformulation of this problem from '95. It wasn't really known, it wasn't used. And the reason for that is that really reduces this problem to this tautological integral, and that was not known how to handle. So if you have a surface and we have, let's pick our types to be this is the square of the maximal ideal on C2. So this is just this L-shaped singularity, right? Whereas it's a monomial ideal. It's a triple point, fat point of this shape. So that somehow this encodes as a node, by the way. So this is one branch, this is the other branch, in some sense, right? So there's a generalization of this observation for more general singularities. Anyway, so for a given singularity, in this case a nodal singularity, you can associate an algebra. In this case, this is the algebra. So this is the algebra, and then you take this geometric subset, which I defined before, where all the types are the same, namely this nodal type, let's say just nodal type. So you see that the length of these individual ones is free. We have S of them, so this geometric subset sits in the Hilbert scheme of 3 S points on S. Okay? So it's kind of a nasty, well, that's a very, very sophisticated object with several different components. But there is a main component which the closure of this. Anyway, yeah, I will not. That needs some further considerations. But anyways, this is a geometric subset sitting there, right? So now if you have a sufficiently ample bundle over S, then the number of S nodal curves in the generic family of dimension S is given by this integral. So that's Götzsche's observation. So you take this, this Hilbert scheme of so this geometric subset over S, which I described, and then you take the top Chern class of this tautological bundle, so L to the 3S. So more generally, if you take, again, the same problem, but we have some prescribed singularities, A1 up to AS, and we can associate, so for any singularity, we can associate such an algebra, and we can do the same. So in a sufficiently ample linear system, the number of these curves is given by a tautological integral. So in particular, we have formally for these counting problems. And finally, because my time is over, just quickly mention this last problem is about the Siegler numbers of bundles over surfaces, and which is basically plays some central role in mathematical physics, but this special number, which is the top Siegler number of this tautological bundle over the surface, it can be generalized for any manifold X, because if you take this over the main component of that Hilbert scheme, you get a similar number. And as I said, for n equals 2, there was Lane, Manfred Lane has a conjecture from the 1990s, which worked out by hand for the generating function of those integrals on surfaces. And it was proved 7 years ago by Vazan, Opera, and Pandit. But in general, a similar generating function does not exist. We worked out the generating function in terms of the dimension, and that actually leads to questions in sort of duality questions in animative geometry between Siegler numbers and Berliner numbers, but this is kind of, that's the motivation for these integrations. But, I'm just let me just summarize this. So I really just show you 4 different examples in animative geometry where the answer can be formulated as a tautological integral. And hence this theory actually, and the theory of tautological integration theory, and hence how we actually use it to integration on non-reductive GIT quotients is kind of central. So I stop here and thank you very much for your attention.
Very much. Any questions?
This may be a bit orthogonal to the second half of the talk, but so on jet bundles, there are these natural geometric structures like the Cartan distribution, which gives a contact structure, and the variational bicomplex, which plays an important role in variational calculus and so on. So I was wondering whether this GIT construction, how does it interact with these geometric structures on jet faces?
I don't think, I don't know. The answer is I don't know. So we never studied these structures actually there. So, and in particular for these jet bundles. Yeah, so no.
Yeah, so question is regarding your jet spaces. So you define JK1N, 1N. So what about F from C2 to Cn or C3 to Cn? Do we have some theory on that? And then
that's a very good question. Yeah. So you can work out that kind of, yeah, instead of holomorphic curves, you can take holomorphic maps from high dimensional fine spaces, right? So holomorphic surfaces, let's say, and isomorphic three-folds. And yeah, you can do the same. There's no, as far as I know, there's no interpretation in like a Hilbert space of points interpretation, but certainly you can work out the non-reductive GRT interpretation. And but I don't know explicit applications of those yet. So, but if you have some idea, that's I really would like to hear.
Okay, thank you.
Any other questions? All right, well then let's thank Gergely for the entire mini course.
Thank you.
Okay, and we.
Oh, by the way, I forgot this. Sorry, but yeah, this is my last slide. No, I'm sorry. Yeah.
Okay, then I have a question. What does that say?
Yeah. Okay. So one more question. You see. Thanks for your attention. Am I right?
I'm not Kannada, but yeah, I think that's.
It's local language. Actually.
The local language. Yeah.
It's not Hindu. It's not Hindi. It's a local Kannada language. So it's not local. It's the local language.
Okay, so we reconvene at 10:50.